Awesome. So we are all here to go. So thanks everyone for coming to this OSU ALT seminar series for the first time for this semester. It's our great pleasure to have Professor Murali Anavaram from USC, University of Southern California, to give us a talk today. So the talk is titled Training Machine Learning Models with Private Data. Before we start, let me give a brief introduction about Professor Murali Anavaram. So Murali is currently a Eliot Hunt Chair Professor in the EC department and also CF department at USC. He is a founding director of this Real Center, funded by Meta. Basically, it's a collaboration between USC and Meta, which is focusing on the research and education in AI and learning. And we're gonna hear a lot of research that is generated from the center today. As a little bit background about Murali, his research is basically tackles a wide range of computer system design challenges, from mobile devices to HPCs and to data centers, you name it. Mainly focusing on energy efficiency, security, and more recently privacy problems. He has been a well-known researcher in computer architecture area. As a key evidence, he has been inducted to the Hall of Fame, if you're familiar with the computer architecture domain, for 3 of these most prestigious computer architecture conferences, ISCA, Micro, and HPCA. He has served as a TPC chair for HPC 2021 and many others. Before joining academia, he has been working with Intel and pioneered the design of the very first 3 microarchitecture design, and have had a lot of achievements. And he is a fellow of IEEE. So without further ado, please.
Thanks, Mi. Hello, everyone. I work in a variety of areas, but today the talk is going to focus on private machine learning. And in particular, we are interested in machine learning with private data on untrusted hardware, basically. How do you use hardware systems capabilities, but not necessarily trust all the hardware's security features? And so that's sort of the focus of what we want to talk about. And so if you look at machine learning today, it has obviously a substantial number of use cases across a variety of industries, from healthcare to e-commerce to transportation systems and so on. And the main reason why this has been very successful, the machine learning as a system, is because they have been using huge amounts of data that is generated by these end users, and that data is then fed to these models. And these models learn from a variety of user data. And if you look at what users today are, majority of the people who actually generate the data that is needed for these models are not ML engineers. They are not the kind of people who understand machine learning models or PyTorch for that matter. And they are probably scientists, or they're people who just generate data but not necessarily be familiar with the modeling itself. So as a result, the machine learning as a service has an is an emerging area where you essentially offload all the complexity to some cloud service providers, let's say an Amazon AWS or Google or Microsoft. All of them have introduced this notion of ML as a service. So basically, the model is in the cloud. You send the data to the model, and the model will learn from the data that you have provided it. And then they also provide you some APIs where you can actually use predictions from the trained model. So you can kind of think of this as a mechanism where the users will send the data, to train the model, or they can send the data to infer from the existing model in itself, and then they pay some, dollars per query or some other mechanism for essentially monetizing this machine learning as a service. And in this particular outsourced machine learning paradigm, so let's just take a look at a very simple inference scheme. Let's say that you have a DNN model hosted in the cloud, and the user has some data. They want to know what that particular image is. So they could image classification or any other tasks that you're familiar with. So they send that information to this cloud service provider with some API, and then the machine in the cloud will return some result back to the user. And these systems in the cloud are a collection of GPUs, CPUs, whatever is the most appropriate computing platform that you can actually deploy these systems in. But the issue here is we are offloading a lot of these computations to the cloud, but can we actually trust these cloud systems to take our data and be respectful of our data and be cognizant of the privacy of this data? And so there are a variety of challenges in this cloud ML setting, which is there's a data privacy concern. So for example, if I send the data to the cloud, will the cloud keep the data private, or it will use for other malicious uses? Computational integrity. When I send the data to the cloud, does the cloud actually compute what it says it is computing? And hence, there are a variety of reasons why you don't necessarily have to trust the cloud servers when you put all of this data into the system. But we still want to use the ML as a service platform. And therefore, there is this tension between sending the data to the cloud at the same time not trusting the cloud. And therefore, we need to figure out a strategy where we can protect the data privacy in the cloud while not trusting the hardware that's inside the cloud. And so that's sort of where we are going to focus on, and that's where the talk is going to kind of look at. And as of now, I have two directions, but if you have questions, please feel free to stop me, and we don't have to talk about both the directions. We can just talk about one and have questions as well. And so there are multiple directions to go in terms of privacy protection and not trusting the hardware in the cloud. One of which is homomorphic encryption. For example, you can essentially encrypt the data and compute directly on the encrypted data. Then there is trusted execution environments, which you probably also heard, hardware mechanism to provide security. And then there is MPC, or multi-party computing, which is an alternative strategy for providing protection by just kind of splitting the data into secret shares and allowing multiple servers to compute. So there are all these directions one could potentially follow. And in this talk, or our work currently focuses on two topics. The first one is on using the trusted execution enclaves. And the second direction we have been focusing is on multi-party computing. So these are the two directions that we have. And time permitting, I'll talk about both. But first, I'm going to start with the trusted execution enclave methodology and how we can use TEEs to improve the privacy of your data in the cloud. So what is a TEE? For those of you who may not be as familiar with the TEE, it's essentially a hardware level isolation provided by certain class of CPUs. But it turns out that it is now available in almost all the CPU settings, including most recently the Hopper GPU allows this trusted execution within the GPU enclave itself. But at the time this research was done, which was a few years ago, mostly it was available on a couple of different platforms. And one example is Intel SGX. And again, if you don't know much about it, please take there's a separate module on SGX that you can read to learn more. But the idea is that you create a isolation chamber within the CPU. And inside that isolation chamber, you put your data, you put your applications, and the machine guarantees that that information cannot be viewed, including by any hackers or even the root users of the system. Like even if you have a administrative capability, you can't see what's inside the enclave because you can kill the enclave, but you can't actually peer into the data or the application code inside the enclave. That's sort of the capabilities of TEE. And so the TEs are great in addition. So you can potentially think of just take the model and you stick it inside the enclave and you run the entire model within the enclave itself. And that would sort of protect your data. But there are problems with that approach, which is that the performance overheads for using this enclaves is quite significant. For example, if you want to run everything inside the enclave, you were limited to CPUs at the time this work was done. But today they have reduced some of those with using GPU capabilities as well. But nonetheless, the performance is not free. The performance overhead is not free. There is a cost to running this stuff in the enclave. And so we needed to basically figure out a mechanism where we want to rely on the enclave, but we also want to use fast GPUs for which there are no enclaves, and we still want to use those GPUs to run and accelerate our training, particularly in the cloud setting. And so the idea, therefore, is that we are going to repurpose the trusted execution environment not to do the full training or the inference. Instead, we are going to perform some minimal computations inside the trusted enclaves, obfuscate the data, and then you take that obfuscated data, which looks like random data, into a GPU and perform the computations on this obfuscated data on the GPU. And then you return the results that are produced on the obfuscated data back to the TEE, and the TEE can still decode that information. So that's sort of this multi sort of collaborative approach. The TEE encrypts the data in some sense, and the GPU computes on that encrypted data and returns the results back to the TEE, and the TEE can decode the results. So that's sort of the goal of what we are going to do. But unlike a traditional fully homomorphic encryption, this strategy is much more efficient and it is pretty robust and easy to implement as well. So let's talk about one of the most recent works that we published on this topic of using TEEs. It's called Dark Knight, which is a theoretically robust privacy protection system within the using trusted execution enclaves. And so that's the work that I want to talk about a little bit. And so what is in the motivation for Dark Knight? The key motivation for the Dark Knight is the following, which is that we can offload computationally intensive operations to the GPUs, and we utilize the TEEs for performing a simple amount of encoding and decoding of the data and performing any kind of nonlinear operations. So that's sort of the key observation for the Dark. I'll talk about a little bit more of the details as we go forward in terms of what does that mean. So Dark Knight basically has 8 steps that I'm going to go through. So the first step is that let's say that you are a user and you have a whole bunch of information that you have, let's say a collection of photographs on which you want to do classification of the images. So the first step is you take all your data that you have and you have encryption on the data and submit all the encrypted data to an enclave, which is shown as a white box within the computer in the cloud. And because the enclave is a sort of a robust isolation chamber, nobody can see what's inside the enclave, and the channel between the user and the enclave is also encrypted, and therefore you can't see what is actually being sent because the data is already encrypted on that channel. So now that the data is encrypted, you send the data to the enclave, and the enclave and the user has, say, a shared private key. You could use public, private, or any other mechanisms, but basically there is some sort of a key that is used. And inside the enclave, there is a decryption mechanism that basically recovers the images that you sent to the cloud provider. And again, now the data is actually vulnerable, right? It's private data, which is now decoded and decrypted, but it's inside the enclave, and therefore it is still protected from any kind of malicious adversary from looking into the data to see what is inside your image. And then the third step is that you take the enclave and you do some kind of a modification of a data. In this case, we are going to do what is called linear encoding of the data using a specialized encoding scheme that I'll describe just briefly in a minute. And once you encode the data looks like random noise at that point. And step 4, you send this encoded data to a collection of GPUs that are attached to your server or could be anywhere in the cloud itself. And these encoded data that is sent to the GPUs will allow the GPUs to operate without any protection at all, because the data itself is not visible to the GPUs. As in the raw data is not visible. So what they see is this obfuscated data, sort of, you can think of it as like a secret shares in an MPC setting. So you can't see what's inside the data. And then the GPUs compute any kind of linear operations, such as multiplying the input with some sort of a model weights to get some computations, and going inside the GPU, which are all linear operations. And GPUs are excellent for doing these kinds of linear operations. Once the data is computed inside the GPU, you return the results back to the enclave. That's when you return the data back into the GPU, into the Intel SGX. And then the way we encode the data and the way the computations are performed, we will be able to accurately decode the results back when you are inside the SGX. And that's something that we can do because of the way we encode the data. The decoding will also be relatively simple. And then we can perform any nonlinear operations on the decoded data within the enclave. And then we do the second layer again, like third layer, fourth layer. So for every layer, all the linear operations obfuscate the data, send it to the GPU. You bring the data back after the computation, you decode it, and then you do your nonlinear, and then send again the linear operations back to the GPU after encoding the data. So this is sort of a iterative process by which we will continue to move forward. So take a look at how this is actually done. Let's say that we have an example of 4 images for which you want to do a classification. I'll explain this with respect to a simple inference scheme, but this can be generalized to any kind of training systems also. But for now, let's look at only inference mechanism. So we have a batch of 4 images, and let's also assume that we have 5 GPUs, which we are going to use to do the computation, which is the inference in this case. And we basically generate a selection of random numbers, which are called the alpha IJs, which are inside the enclave, and these are secrets. And therefore, this is not visible to these. Alphas are not visible to the GPUs or any external entity. And we also sample a random noise R from a large random space, let's say 2 to the power 64 value, which we just sample. And now we are going to show you what exactly are the steps that are happening. So now these images are inside the enclave. I didn't show you the basics of like how you encrypt the data and send it into the enclave, but that's trivial. We use AES or any other encryption mechanisms, and decrypts it. It sees these 4 images, and the goal is to protect these 4 images from being visible to the GPUs. So what do? We are going to encode the data as follows. Basically, you take each of these images, x1, x2, x3, x4, and you use this alpha IJ, which is alpha 1, 1, 1, 2, 1, 3, and 1, 4, and a random noise R. And we combine all of this as shown in this very simple equation to create basically what we call a x tilde 1, which is sort of this obfuscated data that is then produced as an output. And that output is basically sent to the GPU. The key I want you to remember is that this is a linear combination of all the multiple inputs that you have. So x1, x2, x3, we have scaled them with some random numbers and added another random number. And therefore, these are just linear operations that actually happen on these systems. We do the same thing with a different collection of alphas and the alpha 1, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5 to generate a second x2 prime or x2 tilde shown in this picture, and we send it to the second GPU. So these pictures, in fact, what is shown here is actually what is the output that is shown in the real system. These are actually shown from the real system. So as you can see, these look like entirely random noises from the GPU standpoint. It has no idea that these were actually images corresponding to these 4 inside them. So we do this process repeatedly. In this case, we do this for 5 such iterations, and we get 5 combinations, and they're sent to 5 different GPUs. And what did we do? We're essentially doing, if you look at it from a mathematical standpoint, you have 4 inputs, x1, x2, x3, x4, and a random noise R that is shown here, which is the input data. And we have a matrix A, which is the alpha IJs. And all we did was we computed x times A transpose to generate x1 tilde, x2 tilde, up to x5 tilde. So these are the data that are actually sent to the GPUs. So this is relatively straightforward, simple basic linear algebra, and then you get this information. And then what is the GPU computing on? It's computing on these x tildes. And so let's say that it is doing a multiplication with the weight matrices. And so therefore it is going to do W times X tilde. That's what this is done. And what is X tilde? You already know X tilde is nothing but X times A transpose. So this is what the computation has been performed. So this is what the GPUs have computed. And when they return the results back to you, what do you need to do? You need to get WX, not the WX tilde, because I'm interested in actually understanding what the WX are. How will I do that? That's very easy. I just take the WX A transpose and I multiply with the A inverse of that. And therefore, the results that we are interested in can be extracted by just basically doing this A transpose and A transpose inverse multiplication. And then you will basically get your original results back. And so this is the basic decoding process that works in these systems. And this mechanism has a great advantage that the GPUs do not see the X1, X2, X3, and the SGX can still compute the WX after the GPUs have returned the results. So this works well. And the question, therefore, is, can this be used for the same scheme? Can it be sort of broadened for, let's say, integrity checks? So, for example, imagine that you don't necessarily trust the computation from one of the GPUs. Let's say that the GPUs are likely to give you a wrong result. So if you give them, let's say, 2 times 3, they won't give you 6, but they'll give you some random noise added to 6. How do you verify that the computation of the GPUs that you do not trust, in fact, is the right data that they're producing? So again, relatively simple. In this particular scenario, we are actually going to increase the redundancy in the system. So basically what we have is that instead of computing 5 equations from 4 images, we now compute with just 3 images and these 5 equations. And therefore, what we have now, we have 4 unknowns, which is x1, x2, x3, and the random noise R, on which you have computed 5 equations. And what does that mean? We have created a redundancy in my linear computations. And as a result, I can extract the value of WX 2 different ways, right? I can use any subset of 4 GPUs to compute the result. And if the computation from one subset of GPUs of 4, another subset of GPUs of 4, and if they don't match, then I know that there is a potential problem with one of the GPUs. And we don't necessarily need to know which GPU, but as long as there is a then we know that there is a problem. And so it's a relatively fixed overhead, very easy. You just need one extra equation to solve this problem. And now you can detect a potentially wrong or malicious GPU that is actually going to give you wrong results. And so this is basically the goal, is to do integrity checks. We can also handle collusion by essentially dealing with these collusion as, like, basically when you collude, you're essentially trying to remove the noise that is actually presented in the system. How do you deal with collusion? Add more noise. And therefore, we are going to add more noise signals. Instead of adding just a single value of R, we can pick up 2 values, R1 and R2. If you pick up 2 values of R1 and R2, then the 2 GPU collusion will not be able to extract your results. And therefore, for collusion of the GPUs, you can see what we do is we are basically taking a different noise of R1 and R2. And therefore, when these 2 collude, you still cannot remove the noise from the system. So all these are possible. Integrity checks are possible. Collusion is detection is possible. And protection of the data in all these scenarios is still possible. And so obviously this is going to be implemented in terms of an experimental system. So we implemented it on a Coffee Lake, which has an SGX support. We had a bunch of NVIDIA GeForce GTX 1080 GPUs, which we used. And then the GPUs are connected with some sort of a network switch. And we run different kinds of models on this. And so this is basically what the results look like. The results basically show that actually, let me just jump to the speed up. So what we see here is that if I look at the baseline, which is fully inside the TEE and never information leaves the TEE, and you look at what the results of our model execution with the approach that we described, you can see that you're getting approximately 5 to 7x speed up on different kinds of implementations using this scheme, because you're able to exploit the capabilities of our GPUs to do these kinds of computations without revealing any of the data. So this is basically the results that we have. And I encourage you to take a look at our framework with respect to privacy proofs. How do you deal with training? Because this is one of the first papers that not only protected privacy for inference, but also for training. So the backpropagation encoding strategy is described extensively in the paper. And then there is a quantization impacts and aggregation mechanisms, and all the other implementation details are actually discussed in the paper. And I believe we even have some of the code out given to other students and other research groups to explore this dark night strategy in their own research. So that's sort of the focus of what we have done on TEEs. And now let me pause here for a minute if you have any questions on the TEE side before I move into multi-party computing. Yes, Saikat.
Hi, great presentation. So I had a quick question, and maybe you explained it, but I missed it. So I guess I'm kind of confused by how so you are combining 5 images and essentially generating a random noise of those 5 images. Now, when the GPU is returning a result, it will be based on that entire input it's getting and not 5 individual images, right? So how do we expect that the result will be correct, because it's getting a random noise and it will only give you one result back? So how would you separate?
Oh, no, it's not giving one result back. So if you look at this model here, let me go here. So remember, we have sent the information to 5 different GPUs. Each GPU is getting X1 prime, X2 prime, X3 prime, X4 prime, X5 prime. So these are 5 GPUs. Each of them is computing on this infused or this obfuscated data. And you're receiving the results of all the 5 GPUs back into the enclave. And therefore, it's not that there is a single GPU doing the computation. There are actually 5 GPUs computing 5 linear equations. And then you're returning the results back. And therefore, the goal of the TEE is to extract that information from these 5 equations that are actually solved by 5 different GPUs.
Okay. And I think previously you also mentioned something about that it's doing like a layer-wise computation. So you do the first layer, you get a result, and then you do the next layer. So is the particular forward pass as well?
Yeah, so in this forward pass, what I showed you is just think of it as like one pass, right? Like this is one layer of the forward pass, and the results are returned back. You decode the result, you apply ReLU or whatever nonlinearity you have, and then you generate a new set of values that will become your new X1, X2, X3, X4, which are sort of the intermediate activation maps. And then you apply them down to the next layer, and then you kind of repeat this process over and over again for all the layers that you have. And that also brings me to the question that Mohammed actually asked, which is, hey, why are you encoding this data if I can just do the encoding itself on the client itself? Which is a good point. And in fact, one could potentially not use the enclaves and have the client itself do this composition or obfuscation and send it to the GPUs. But the main reason why we use the TEEs is for the purpose that TEEs are in the cloud, GPUs are in the cloud, and they can communicate with each other much more efficiently than if I were to communicate with this client, which is a mobile phone in the wild, and it's not possible for potentially for this mobile device to do all of these computations. So there is nothing fundamentally limiting in it, but there are a lot of practical limitations of bringing this encoding pass directly into the client. Instead, we use the TEEs to do that. But if you have an extraordinarily high bandwidth between your client and the GPUs, you could do this as well. Hopefully that answered your question, Mohammed. Okay, so now let me kind of jump in a little bit and talk about our most recent work, which is the multi-party computing. And this is work that we have been working on for a while. And the goal here is to show that an alternate strategy exists for protecting the privacy, which is based on MPC. So what is MPC? MPC is basically allows a secure cloud computation protocol where you can essentially not trust the cloud at all. And in this case, not even the TEs. I don't trust anything. And we are going to do some computations on this untrusted clients. And how do we do that? The way you do that is the client who has a secret that they don't want to disclose to the parties, they will share that secret. They basically take that important information, create two secrets and send it to the two parties. And the parties operate on those secrets, which means they know nothing about the original data. They compute the results and they return the results back to you, the client, and the client can fully recover the computation output from this secret shares of data that is actually obtained. Okay, let me show you what is in the MPC setting. So imagine that you want to compute W times X, which is sort of, again, your machine learning model-like approach. And you have two parties, P1 and P2. And you want to compute WX on these two parties because you don't have the local computation capability to do this, perform the computation. So we're going to secretly share the W and X. So you see there is a secret share of W called W1 and a secret share of X called X1, which is this values that are shown here. And then the same one, W2 and X2, is shared with the server 2. What is X1 and X2 and what is W1 and W2? Well, it turns out that you take the original data and you generate secrets from that original data using what we call a secret sharing mechanism or secret sharing generation. There are two different ways of secret sharing. One is called additive secret sharing. The other one is binary secret sharing. And then I think there's a third one called YAW secret sharing, which we won't focus much on. But let me just show you what additive secret sharing is. You have in value X that you want to share with two clients and without disclosing the value of X. So you take a random number R, you sample it from some large random space, and you get a value of R. And then you take the same R, you subtract from the X, and you get X1. And now you take this X2 and give it to one client or one party, and you take X1 and give it to another party. So now you have these two parties getting these two data segments, and that both of them look random because R is random, therefore X minus R is also a random value. And so with this in mind, how do we compute on these secrets? So we're going to use something called Beaver triple assisted computation. And what is a Beaver triple? Again, it's a collection of random numbers. You pick two random numbers, A and B, times B, and this is called the Beaver triple. Basically, it has two random numbers, and the product of those two random numbers is a third random number. And we are now have three random numbers, A, B, C, and two inputs, X and Y. And we are interested in computing X times Y. At the beginning, we will do the secret sharing of X and Y, A, B, and C as shown here. And how is this done? It's additive secret sharing. X1 is equals to X minus R, X2 is equals to R, same with Y1, same with A1, A2, A1, B1, and C1. This is standard secret sharing mechanism. And then what do we do? The first step the two parties will do is they will compute what is called the local deltas and local epsilons, which are basically X1 minus A1, Y1 minus B1, and then they also compute and they already have the C1. So this is again locally compute. And the second step is you broadcast. So the party 2 will broadcast delta 2 and epsilon 2. Party 1 will broadcast delta 1 and epsilon 1. And so both sides get the other side's deltas and epsilons. And remember, these deltas and epsilons are also secrets because there's no information about the original input in these deltas and epsilons because it's all uniformly random. And then what happens is that each party sums their deltas and epsilons that they receive. So they take the delta 1 plus delta 2. The other party will also do delta 1 plus delta 2, epsilon 1 plus epsilon 2, epsilon 1 plus epsilon 2 on party 2. You get these global deltas are what we call the open data that you got. Again, remember, x minus a is random, right? So in the end, even if you compute the summation, this looks entirely random to you. Epsilon also looks entirely random to each party. And now the next step in this system is we basically do these two computations, Z1 and Z2. You can see this is just a basic linear algebraic equations. And once we compute this Z1 and Z2 on the two parties, and when you sum the two results, and you can work through this equation, and you will see that basically C, remember, C is equals to A times B. That's the most important part. And once you do that, you can see that it simplifies to X times Y. And therefore, two parties computed Z1, Z2 without knowing anything about X and Y. But when the client receives the data and they sum the two results, they get X times Y. And that is the key of multi-party computing. And multi-party computing has been in existence. This is all great. It requires no trusting of entities. It provides excellent security guarantees or privacy guarantees. But what's the cost? It's not free. And so what is it that it is going to be? So we have basically wanted to learn the cost of MPC in the setting, in a cloud setting, and see how expensive is this MPC setting and where the bottlenecks are. And so we did some studies. Basically, we picked up some large language, not necessarily large language models, but natural language processing models for this particular work. Why? Well, NLP has a lot of private information, right? Like voice and our own writing and text and all of it. So we wanted to use this as sort of a driver to see what these systems provide. And then what better than to pick up transformers, which is basically a very well-known exemplar NLP model. So we picked up a transformer-based models, and the transformer-based models, I'm sure many of you know, essentially looks like this. This is one layer of a transformer. There is a certain amount of matrix multiplication followed by dot products and some softmax computations. This is the sequence of data operations that are performed. And in MPC setting, you can essentially give all of this information as two sets of secret shares. Basically, the VKQ is split into two matrices of V1, K1, Q1, V2, K2, Q2, and your input is also split. And then you provide this information to the two multi-party computing servers. And we run the computation in the MPC setting. And there are just a couple of important notifications. In an MPC setting, typically to compute e to the power x secretly, because x is a secret, they typically simplify that using very simple sort of a Taylor series like expansion using this equation. Similarly, reciprocal is computed using this very simple approximation or a simplification. So those are the two things that they do, just to keep that in mind. And then we implemented this entire thing on our experimental setup, which contains a bunch of GPUs. And we picked two NLP models, XLM, which is a 12-layer transformer, and VIT, which is a 12-layer transformer model that so this is sort of on the image classification side of things using NLP frameworks. And so we ran that experiment to see where the costs are. So this is what was surprising to us. So if you look at the total computation time in plain text, you see that the result says 4.25 seconds. So let's just focus on XLM. It doesn't matter. The results are very similar to the VIT as well. So it was about 4.25 seconds when we were actually doing in plain text. But when you do this on an MPC, this 4 seconds explodes into 58 seconds. So there's a substantial slowdown when you try to take these MPC protocols and apply to these large-scale language models to protect the data. It's not free, in other words. And so there's a cost, and the cost here is roughly an order of magnitude. And then we look at where this complexity comes from, or why is this slowdown? And it turns out that the biggest slowdown comes from computing the ReLU and the softmax operations in the MPC setting, which is basically 30 seconds almost of the 58 seconds. 30 seconds are spent on softmax, and about 9 seconds are spent on ReLU, which are the big increases. Matrix multiplication increased from 4.25 to approximately 8.2 seconds. That's about 2x. But the thing is, the ReLU and softmax took so little time in plain text, But when you do them on your MPC server setting, substantial explosion in the cost. And most of the explosion in the cost occurs because there's a massive amount of communication that goes back and forth between the communicating parties. You remember I showed you in the previous slides that delta 1 and epsilon 1 are broadcasted back and forth. That exactly happens, but in the case of ReLU and softmax, that happens many a times, and that communication cost eats into substantially into your overall execution latency, and therefore you see a substantial slowdown in these systems. And so this is sort of the reasoning, a little bit more of the reasoning. Why is that the case? If you look at softmax, softmax is obviously, you already know, it's basically this equation. But in reality, softmax is computed using this equation, because when you compute an xmax, which is the maximum of a large vector, you get a much more numerically stable softmax, because you are basically normalizing the values of this vector, which have a whole collection of random values, large range of values. And so you can basically subtract the xmax and you can get a much more robust computation. But in order to get robust softmax, you have to compute max. And the max computation is a substantially problematic cost in an MPC setting, because you have to transform additive shares to secret shares, additive shares to binary shares, and do all kinds of computations to essentially compute the maximum value of a set of numbers. And that is the reason why you see a substantial slowdown that we actually showed in the previous slide. And so this is sort of the reason that we see as a big issue. I know it's already at 10:50, so I won't go much more into the detail, but we have the remarks I want to make here is that MPC is great, but the protection comes with a cost, an order of magnitude slowdown in your results or latency. Approximations are numerically unstable, and therefore you need some way of robustly producing these results. And techniques for reducing the MPC cost is also very important. And we have, in fact, been working on that exactly. I don't have the time to go through today, but because I was sort of too ambitious, thinking that I might be able to cover it, but I won't have that ability. So I'm just going to show you the MPC pipe, which is a latency a mechanism to reduce the latency of multi-party computing. And we have some extraordinarily interesting results on the MPC pipe. We have done a whole collection of, but the basic principle is very simple. In MPC pipe, you take computation and you take communication, and currently they're all serial. You make them parallel, concurrent. That's the basic goal. The basic goal is to take the compute, take the communication, and make them concurrently happening at the same time. If you do that, you substantially improve your overall performance. And so, unfortunately, I won't have a whole lot more time to go through that. So I'm going to sort of skip over all the results, all the discussion. And all I will say is that this MPC pipe gives you substantial improvement, both in terms of throughput of about 30% throughput and 10 to 15% improvement in latency. And I will leave that with the final thought that privacy is going to become an even greater challenge. Performance can no longer be the only key driver. One has to consider the privacy and security implications of machine learning. And as we demonstrated, that MPC is a great, secure theoretical solution, but there are costs associated with it. And therefore, as systems researchers, we have to kind of take that theoretical knowledge and figure out how do you actually build systems to reduce some of those costs. And even though I didn't talk about MPC pipe, that's sort of one direction by which we can sort of take an existing MPC system and reduce the cost of that MPC training using this pipeline mechanism. And so with that, I'll say that this is my research group, and we obviously can't be doing this presentation without the help from many of these students who work in my group. And so with that, I'll stop here. And I know that there's one more question. I think on the previous part of the talk, which is, it says that from the privacy perspective, does the nonlinear layer such as ReLU contain more information and have more leakage compared to linear computations? I don't think that is true. The information leakage is pretty much across every layer. There is a certain amount of information leakage, whether it is linear or non-linear. I don't think there is a specific requirement that non-linear layers give you more leakage. So it's not related to the linearity. The leakage of information is not related to the linearity. But the reason in the previous work we bring the non-linear computations into the enclave is because if you apply ReLU in an encoded space, you can't decode it. That's the reason why we use the enclaves to do your ReLU operation, right? That's the reason. And therefore, we can't actually apply ReLUs on encrypted or encoded data space because it's harder to recover the data. Although there are some new techniques that people have been looking at, but in our methodology, we said, well, any nonlinearity, we let the GPU decode the data and then compute. And so that's what we did. So I'll take
Awesome.
any additional questions you may have.
Yeah. Any other question from the audience? All right. So I have a question. So, you know, for the first topic about TEE, if I understand correctly, so the clients, in your case, probably can be mobile devices. So they have to send in their data, right, to the cloud at first place. And by doing that, the assumption is that you trust the clouds to some extent because you send the data to them. Is that correct?
So when you talk about, so in the first part of the presentation, the clients send the data to the cloud. The only piece of trust we have is the enclave. We don't trust anything other than the enclave. We don't trust the computers. We don't trust the outside of the enclave, anything. We don't trust the GPUs. So the only enclave is trusted. And that's the reason why we are willing to send our input using a key that I shared with the enclave. And you encrypt the data and you send it into the enclave. And therefore, the channel is encrypted. And once inside the enclave, the data is clean, is not going to be leaked. And therefore, our trust in that model is limited to the enclave in itself.
I see. So I'm assuming like there are like more and more mobile devices today. They already have some TE, right? Like, or maybe in the future, like more advanced mobile devices. So if that is the case, so they can do something you mentioned from the cloud. Actually, you can do that on the devices, so that you can avoid.
Right. So it's really, there is no, I think there was a question posed, I think Muhammad, I think posted the question, which is, oh, I don't need to go to the cloud enclaves. Instead, I can do some of these encoding mechanisms inside the edge devices itself. That is certainly true. But the advantage is offload this information to the enclave, then all the 152 layers of ResNet can all be just communicating between the enclave and the GPUs without the client or the edge node participating in every single one of those transactions. And therefore, the assumption here is that as an end user, you don't want your mobile device or an edge device to participate in all of these computations. Maybe it's a different mindset in a federated learning setting, but in this particular setting where we are interested in having the cloud do most of the work, we are not going to do that sort of encoding and decoding on every layer, right? It's not like you do it once and you submit it. You have to come back after one layer, the second layer, and so on and so forth.
Yeah, that definitely makes sense.
Let me read this question that Muhammad posted, which is, I had a question about the trust in the TEE and MPC. So in MPC, the user does not need to trust anyone. But in TEE, the user still trusts the hardware provider of the TEE. That is correct, Mohammed. So in the case of MPC, the only trust boundary that we cannot cross is that it is possible for the clients to for the parties to collude. So we have to know that limits of collusion, like how in the examples that I showed you, I said there are two parties receiving the data. So if you look at this, in this slide, I showed you that there are two parties getting X1 and X2. Obviously, if these two parties collude, they can just send X1 to one person and X2 to the other person, and then they add up X1 plus X2, they get the original X, right? And so there is no protection if these parties collude. But the parties do talk to each other. There's no problem with talking to them. In fact, they broadcast and they talk to each other. But the broadcasting of the data has nothing to do with the communication of the secrets itself. It's only communicating random noise so that they can get to that X minus A, the delta and epsilon values. And hence, you do have to make the assumption that the parties do not collude. But if there is a collusion, MPC can handle the collusion by essentially secret sharing more broadly. In other words, instead of even if two people collude, let's say that I created 3 secrets and I give 3 secrets to any person. If 2 people collude, I don't still disclose anything else into the system. And therefore, it is possible for the systems to be built with a limited amount of collusion, or actually more precisely, with a known amount of max collusion. And therefore, if I say 2 parties can collude, I know how to build the corresponding system. If you tell me there are 3 parties are going to collude, I will tell you what the system is. So I think this is sort of the model that we are currently exploring, which is these parties do not collude in this setting. The other thing that I also need to mention is that these parties also are semi-honest, which means that when they compute this X1 minus A1 and X2 minus A2, and then they're broadcasting with each other, we assume that they're producing the right result. That's the reason why this computation will actually add up to X times Y. And therefore, this X minus Y A and Y minus B are under the assumption that the parties are semi-honest, which means that they are doing the right computation. They won't mess with the computation itself. And in fact, we just gave a presentation this morning where we talked about a more robust setting where I don't trust the 2 parties also to do the computation, in which case they can actually add noise to the computation and send the results. And there is a whole new strategy to deal with that, which is called tag-based computations, which is also a well-known MPC strategy. And we have some techniques to reduce the cost of tagged-based multi-party computing as well. But that's not something that I covered today.
Awesome.
And then it says, is there a specific location limit between the MPC parties? Yeah. So, Mohammed, the only requirement is that the parties cannot collude. How you do it is up to you. For example, I can take one client in the Google cloud and another client in the Amazon cloud, and that will give me a relatively strong robustness guarantee. But if I trust that 2 racks in the same data center are also equally isolated, I can use those also. So there is no specific location limit. The location limit is simply, does that allow for easy collusion? And in general, the closer the parties are, and therefore it's, from a practical standpoint, more likely than not that you put them sort of physically separated so that they are some isolation that you create.
Okay, awesome. Any other question from the audience? All right, I think we are pretty on time. So yeah, again, thanks so much, Murali, for the wonderful and fantastic talk. We have, I believe the audience and I have learned a lot. And yeah, thank you for sharing all these experiences, this knowledge to us. Yeah, so let's conclude today's seminar, and we're gonna see everybody next time then. Thank you, Murali, again. Thank you.
Thank you, everyone. Thanks, me. See you. Bye.
See you. Bye-bye.